Hello everyone, I am Rahul Madhawani from VIT and me and my friends are here to explain you the IEEE standard for floating point representation. So this is the content of our today's topic. Introduction to floating point. Floating point is a way to represent the real numbers in hardware. Floating points are important data type in computation which are extensively used. Without them you won't be able to calculate the numbers which are up to decimal places. But how does the hardware save and processes it? So let's see it.
Integer, the decimal number is converted to its binary and stored in the memory. For example, if you want to store an integer, let's say 39 in the computer, we take binary of it, that is 100111, and in binary bit it will be 13, 32, 16, 8421. So that will be 32 plus 4 plus 2 plus 1, that is 32 plus 7, which will at last be 39. So this is how you store a decimal digit in a binary language. Binary arithmetic is used to process and operate these numbers. The largest positive number that can be stored in 8-bit is 255, in 16-bit is 65,535, and in 32-bit it will be 4294967295, which is quite large. But integers are most commonly used for counting purposes. But we use real arithmetic fractional numbers in most of the scientific computations, so it was necessary to process these type of numbers.
Now let's see representation of floating point. While representation of floating point, we need to decide how many bits are required to store. Normally in engineering, we need precise up to 7 to 8 significant digits. Now let's see what is mantissa and exponent. The mantissa is the fractional part of a common logarithm, that is the base 10 logarithm, which represent the digit of the given number but not its order of magnitude. And the exponent is the component of a finite floating point representation that signifies the integer power to which the reduction is raised in the determining the value of the floating point representation. These are some examples. First, 5 into 10 is raised to power 2. Here mantissa is 5, base is 10 and exponent is 2. Similarly, in the second example, here is mantissa is 234, base is 2 and exponent is 43. Third example is quietly different. Firstly, we have to convert decimal form into integer form. Then the mantissa is 36453,746, base is 10 and the exponent is -4.
Single precision format. Single precision format uses 32-bit memory. 1 bit is for sign, 8 bits are for the exponents, and 23 bits are for the mantis. Let's take a simple example to understand it more clearly. Now the example is to represent 343.125 in single precision format. The first step is to convert the decimal number to binary. After converting the decimal number to binary, we have to normalize the number. That is to compare it with n into 2 raised to e minus 120. Now by using the format, we will find the values of e and n. E means the exponent and n means the mantissa. After finding the values of e and n, our step 4 will be to represent the values.
Double precision format. Double precision format uses 32 bits memory. 1 bit 63 is for sign, 8 bits 52 to 62 for the exponents, 52 bits 0 to 51 for the mantissa. Sign 1 bit, exponent 11 bits, mantissa 52 bits. We will take same example for better understanding.
Now we will understand how to convert a decimal into double precision format. By taking a simple example, we are taking the same example which we understood for the single precision format. So let's take the same example, 343.125. We have to convert in double precision format. So for converting, the step 1 is convert the decimal number to binary. Convert the decimal number which is left of the decimal separately and which is right of the decimal separately. So we know how to convert 343 into binary, it will be 1010101111. But if you don't know how to convert a point number into decimal, so I will show you. Just take multiply. Yeah, I want this pen with black color. Just our number was 0.125 multiplied by 2, so we will get 0.25. I got 0.25. So I got 0 to the left of the decimal, so I wrote it 0. When we again multiply 0.25 by 2, we will get 0.5. In 0.5, we will also have 0 to the left of the decimal, so I wrote 0 here. Again, when we will multiply 0.5 by 2, we will get 1. We will get 1 to the left of the decimal, so I wrote 1 here. So our binary is 001. Hence, the binary format of 343.125 will be equal to write 343's binary here and add binary of 0.125 by taking a simple decimal point here. So now we have the binary of this whole number. Whole number means a decimal number. So now we have to compare our decimal number with this format, 1.n format. So we have to shift that decimal by how many? 1, 2, 3, 4, 5, 6, 7, 8. By how many? 8 digits. We have to shift that number to left. So our number will be, it is in next slide, so I will show you the next slide. So it is, we shifted the decimal by 8 digits, so our number is 1 point, and this number 01010111001, this whole number, our format was 1.n into 2 to the power e minus 1 0 2 3. So we will compare our number with this format. So we will separately got the value of n. The value of n is nothing but this number. This whole number is value of n. So we will just take the value of n as it is. Now e 2 to the power 8. The 8 will be equal to e minus 1023. So from that equation we get the value of e, which is 1023, and the binary of 1023 we can easily calculate. So the binary of 1031, sorry, by mistake I pronounced wrong. So the binary of 1031 will be this much, and that e value is our exponent. Now we are only remaining with representation of double precision format. Double precision format representation. We know always the MSB, most significant bit, represent the sign of the number. So our number was positive numbers, and we know very well that if a number is positive, then the MSB is always 0 here. And exponent, we calculate the value of exponent. Just make sure that exponent will be always an 11-bit number. So just count that number: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if you want to check our answer is correct or not, we can just count the number of exponents, number of bit of the exponent number. If it is 11, just make sure you are correct. And now we will represent mantissa here. Our mantissa is also an 11 bit, but the number of bit of mantissa doesn't matter because the number of bits of mantissa is 52 bit. In our answer we got 11 bit number. So we will just write 11 bit number and follow it by dot 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 00 dot dot dot. It means we will just completing the 52 bits by adding 000 to it. So in this way we easily converted our decimal number into double precision format. I hope you all are understand with this now.
Thank you, Group 11.